All right, ladies and gentlemen, welcome back to AP Chemistry with Mr. Kenton. Glad you guys are joining me. We're going to be continuing our work within Unit 4 of AP Chemistry, and we're going to be focusing in today at really two topics. We're going to be looking at types of chemical reactions, and then we're going to focus really on two of those three types that we're going to introduce by looking at metathesis reactions as well as acid-base reactions. Okay, and so we're continuing along in our discussion of Unit 4 and looking at types of chemical reactions. And as you can see here, this corresponds to Chapter 3, Section 2, and then it's also going to correspond to Chapter 4, Sections 2, 3, and 4 specifically. Okay, so let's go ahead and dive right in, and let's talk about the things that we need to understand and hopefully be able to identify the things that you should be able to do after you look at this video. All right, so here we go. Types of chemical reactions. And so like I was stating earlier, there are three broad categories that reactions are going to fall into. Those three categories are exchange or metathesis reactions, we have acid-base reactions, and then we have oxidation-reduction reactions. Now, my goal with this particular video is I'm going to focus in on those first two. We're going to make a separate video that looks at oxidation and reduction. Now, please, ladies and gentlemen, don't forget the classifications that you learned in honors chemistry, like single replacement, double replacement, synthesis, decomposition, combustion. Those are all useful tools, but what we're going to see is that each of those that I just stated could fall into one of those three that are listed here. So with that being the case, you can certainly use those other designations like synthesis or combination, decomposition, combustion, double replacement, single replacement. Certainly you can use those names, but I want you to begin to make a transition and think of how do those different types fit into one of these three categories specifically. All right. Now we're going to start by looking at exchange or metathesis reactions. All right. So when we talk about exchange or metathesis reactions, this is going to encapsulate your double replacement reactions. Okay. And when you think about it, a double replacement reaction can be identified by looking at the following changes that occur in a solution. Now, I think this is important that it did mention we're talking about solutions that are reacting here, right? So you've got reactants that are aqueous. Now, it is possible that you can have reactants like an aqueous reactant and a solid, and you can still have a metathesis reaction. But certainly those are possible, and we'll see the different examples that I've got listed here below. But for a metathesis reaction, what I want you to consider, things that you need to identify that you should be able to see that take place during this process, is precipitation could occur. And what I mean by that is you've got two aqueous solutions, you mix them, and then a product is formed that is a solid that's insoluble in that solution, and therefore it precipitates out. It falls out of its ions, they combine, and they form a solid that's going to then settle at the bottom. Okay, a second thing that could happen in a metathesis reaction is a weak or a non-electrolyte gets formed in the process. Now this is important because you're thinking about it within the context of particle representations. We've made a big deal in this particular unit about looking at reactions from a particle perspective. And so if you get the formation of a weak acid or a weak base, or if you get the formation of a non-electrolyte, that's going to be an indication to you that a metathesis reaction has taken place. And then lastly, another metathesis process is when you get an insoluble gas that's being formed as a reaction is taking place. Now, I've tried to provide you with the most general form of a metathesis reaction, and you can see it here. You've got AX, AQ plus BY, AQ, is going to form let's just assume that AY is our soluble or is our solid substance, and BX is our substance that's remaining aqueous. Okay, and when you look at each of these examples that I've given you, I've tried to provide you one that follows kind of these particular patterns that I mentioned above. So in this first one, you've got two aqueous solutions, they mix, and you get the formation of something that is aqueous, but then you get an insoluble solid that is being produced over the course of that metathesis process. Okay. If we look at the second reaction that I've listed, you've got hydrochloric acid and sodium hydroxide. You get the formation of water and sodium chloride. And as we can see here, this process, rather than an insoluble solid, we're getting a non-electrolyte that's being formed, which in this case is the water, right? So water is a non-electrolyte, and sodium chloride, strong electrolyte. So the non-electrolyte water is the driving process in this particular case. Now, this one's a little bit special because we're dealing with acids and bases, and so we'll talk about acids and bases a little bit more here later. And then the last reaction that I've presented to you here is you've got hydrochloric acid reacting with sodium sulfide, aqueous solutions, and then we get solution of sodium chloride, but then we get an insoluble gas, and so hydrogen sulfide, H2S, is not very soluble in water, and so it's going to precipitate out, if you will, as a gas. It's going to produce gas bubbles. They're going to escape into the air, right? So in this case, we've got that insoluble gas that's been formed as a result of this particular process. And so hopefully that gives you some examples that you can look at that show those different types of metathesis processes. Now, again, within your double replacement reactions, one thing that I would like to mention has to do with solubility rules, right? And so with precipitation reactions, as we've seen, it involves the mixing of ions in an aqueous solution, and ultimately it's going to produce an insoluble or a sparingly soluble ionic compound. And so that's where our net ionic equations came into play. We used those to help us to be able to identify what was really the driving force in that particular chemical process. Now, as it pertains to these solubility rules, instead of having to rote memorize every single solubility rule, AP wants you guys to know the following: that if you have a sodium-containing compound, if you have a potassium-containing compound, an ammonium-containing compound, so NH4, plus and nitrate salt, so an NO3- containing compound, all of those will be soluble in water. Memorize that specifically, and that should help you with anything that's a solubility-related question on the AP exam. I hope that makes sense, right? Now, we're going to shift gears now. We just dealt with the metathesis processes, and now what I want us to take a look at are acid and base reactions, okay? And in order for us to do that, we're going to be examining things from Chapter 4, Section 3, but then we're also going to dive into some things that are in Chapter 16 in Sections 1 and 2, okay? Now, for most of us, you're probably coming into AP Chemistry maybe remembering the Arrhenius definition from honors chemistry. And if you don't, that's okay, because I'm going to give it to you right here. So the Arrhenius definition communicates to us that an acid is a substance that when you place it in water, it produces hydrogen ions. Okay, so an acid in the Arrhenius definition is a substance that when you place it in water, it's dissolved, and it increases the concentration of the H+ ion that's present. Now, in the Arrhenius definition, a base is a substance that, when dissolved in water, produces additional hydroxide ions. So it increases the hydroxide ion concentration in your solution. So that's kind of the working definition that I imagine most of you are bringing to the table. Now, when we think about this, how do we define some things as acids and bases? That's when maybe the pH scale is something that we can use. And so the pH scale it gives us a way to determine the amount of H plus ions that are in a solution. Now, you're probably familiar with this, but that when you have a solution where it has a pH that's less than 7, we would classify that solution as being acidic. If the pH of a solution is greater than 7, then we would classify that solution as basic. And then if the pH is equal to 7, we would say that that solution is neutral. Now, when we make these claims, talking about these pHs and using that particular scale, it's important for me to communicate, ladies and gentlemen, that this is only true at 25 degrees Celsius. And so I mention this because if you start to change the temperature at which you're dealing with your solution at, the scale is going to shift a little bit to where 7 may not be neutral, okay? And so you might have a larger range of pHs that are acidic or a larger range of pHs that are basic. That's going to depend on the temperature of your solution. Now, for our intents and purposes, at least for right now, we're going to be operating under the assumption that we're working at 25 degrees Celsius. So at 25 degrees Celsius, pH of 7 is neutral. So if they indicate that it's at a different temperature, then just remember pH might not be 7 at that new temperature. Okay. So that's our Arrhenius definition, right? Increasing H plus or OH minus ions is what's going to determine whether or not something is an acid or a base. So for example, hydrochloric acid, when it's placed in water, it's a strong electrolyte. So it's going to increase the amount of H plus ion that's in solution. Another good example, sodium hydroxide. When sodium hydroxide is dissolved in water, it produces hydroxide ions. So it increases that OH minus concentration, so therefore it's a base. However, there are other definitions that we need to consider that help us in our understanding of acid-base reactions. And so in order to do that, we're actually going to be examining what's known as the Bronsted Lowry definition. And this is where, moving into chapter 16, is where you're going to find this information. So the Bronsted Lowry definition of an acid and a base are as follows. So an acid, according to this definition, is going to be a substance that donates a H plus ion in solution. Now, the donated H plus ion can also be referred to as a proton. Okay, so an acid, using the Bronsted Lowry definition, is a substance that donates H plus ions. Now, a base, a Bronsted Lowry base, is going to be a substance that is going to accept H plus ions from another substance. Okay, now using this definition, hydroxide ion is no longer needed in order to classify something as a base. And this is true regardless of what we're looking at, because we can look at substances that are basic, but they don't contain that hydroxide ion. And so the Bronsted Lowry definition allows us to expand that to encompass more reactions that are truly acids and bases. Now, I've listed here for you guys an example of something to consider. We've got the reaction of hydrogen chloride gas with water. And what we can see happening is that in that process, the hydrogen chloride gas, the hydrogen chloride, donates an H plus to water, and then the water accepts that H plus. So for us, our Bronsted Lowry acid in this reaction would be HCl. HCl donated H plus. In this case, water is a base. It accepted that H plus that the hydrogen chloride gas was donating, if you will. And then you got the formation of H3O plus, which is hydronium ion, and chloride gas. Now, again, we just listed that. HCl is our Bronsted Lowry acid, and H2O is our Bronsted Lowry base. And then we get the formation of H3O plus, which is that hydronium ion. Now, again, I mentioned this expands our definition of acids and bases. And so with the Bronsted Lowry definition of acids and bases, acid-base reactions are no longer confined to simply aqueous solutions, which is important from a chemistry standpoint. Now, something else I want you to consider about water. Water's kind of unique in the sense that it's amphoteric, and amphoteric means that water can behave as either an acid or a base. And so when you think about it, water can gain an additional proton or it can donate a proton, because it's very possible that the water could donate a hydrogen so that it forms hydroxide ions. And so water is not the only substance that's amphoteric. It's just one that's really important for us to consider right now. So again, amphoteric means that a substance can behave as either an acid or a base using the Bronsted Lowry definition. All right, now that's going to lead us into a discussion of conjugate acid-base pairs. So the Bronsted Lowry definition, as we've seen, talks about this idea of donating or receiving protons. And as a result, you can get a conjugate acid or a conjugate base that gets produced over the course of that acid-base reaction. Now, for weak acids and bases, for example, so something like ammonia or even acetic acid, right? Those are both weak acids. Well, acetic acid's a weak acid, ammonia is a weak base. When they react, we know they exist in an equilibrium. So instead of it being kind of a single solid arrow that goes in one direction, it exists in equilibrium. There's this moving back and forth between the reactants and products that can take place. And so what we can do is we can generalize an acid-base reaction that's following the Bronsted Lowry definition using the following expression. So you've got HX, in this case that would be it could be your acid, you've got H2O as your liquid, and then you've got the formation of X minus, which would be here, and H3O plus AQ, which would be the substance the water that gains that additional proton. Now, in looking at and analyzing this general expression, HX and X minus have a specific relationship. HX is what donated the proton, X minus is what was left over after the fact. So HX was our acid, but its conjugate base is X minus. Okay, because X minus was the substance that was left over. Now, in this reaction, H2O and H3O plus are related as a conjugate acid-base pair as well. H2O is going to be the base. It's the substance that received the hydrogen. And then H3O plus is an acid using this Bronsted Lowry definition. H3O plus now has the capacity to be able to donate a proton to X minus. Okay, and kind of a quick summary of kind of how you define those terms, conjugate acid or conjugate base. The conjugate base is the substance formed when a proton is removed from a Bronsted Lowry acid. And your conjugate acid is the substance that's formed when a proton is added to your Bronsted Lowry base, right? And so again, that's why HX was the acid, X minus is its conjugate base. H2O is a base, H3O plus is a conjugate acid. I hope that makes sense. Now, the last thing that we need to look at are the strengths of these conjugate acid-base pairs. Now, here's what we need to recognize. The stronger the acid is, or the stronger the base is, the weaker its conjugate base will be. So what that means for us is that our strong acids and strong bases form very weak conjugates. So the conjugate base of something like chloride ion, for example, as you can see over here in this chart, Cl- as a base is very weak. If you think about this, the reason for that, chloride, when it has that Cl- that's available, it doesn't really want to receive an H plus and become HCl, right? And if you think about bases, bases are proton acceptors. Well, HCl is a strong acid. It doesn't want to go back to being HCl. It wants to stay a Cl minus. Same thing's true for something like sulfuric acid. When it forms HSO4 1-, it doesn't want to go back to being sulfuric acid. It wants to stay in this particular state. Same thing with nitrate, nitric acid. When nitrate is in solution, once it's there, if there's H plus present, it's not going to want to go back to being the molecule HNO3 because it's more stable once it's broken down like that. Okay. Now, for some reference here, you can use this table to kind of recognize your strength, right? And so what you start to see is that something like a weak acid like HF, well, we start to see an increasing strength in its conjugate base. You know, you move down here, you move to acetic acid, right? That acetate ion is a stronger base than F-. Or if you've got something like the hydrogen carbonate ion, well, carbonate as an anion is actually a pretty strong base. That's why carbonates are basic in solution, right? So H plus is the strongest acid that can exist in equilibrium aqueous solutions. That's going to be important as we talk about equilibrium later on, right? Hydroxide ion is the strongest base that can exist in equilibrium aqueous solutions. It's also going to be important as we shift into equilibrium reactions much later. Now, as a result, when you start to look at conjugate acid-base pairs and their strength, it's important to recognize that in every acid-base reaction, the position of the equilibrium is going to favor the transfer of a proton from the stronger acid to the stronger base. Now, that might sound a little bit confusing, but equilibrium processes, even though there's going from reactants to products and there's the ability to move forward or reverse, equilibrium reactions are always going to favor one side over the other. And for acid-base reactions, the substance that's going to be that's being formed is always going to be due to the fact that the strongest acid donated its proton so that it could form the stronger base, right? So hopefully that makes sense. And I'll just say that again. It's always going to favor the stronger acid being able to transfer a proton so that it can form the stronger base, right? It's never going to work in a situation where the weaker acid is going to be able to transfer its proton to something to make a base. I hope that makes sense. And ladies and gentlemen, that actually is going to conclude this particular section or this particular topic that we needed to go through. We were able to look at our metathesis reactions and our acid-base reactions. We were able to look at kind of the components that we can identify in a metathesis reaction to let us know that we have one. We looked at acids and bases. We looked at the Arrhenius and the Bronsted Lowry definition. And then we looked at conjugate acid-base pairs. And so you should be able to identify Bronsted Lowry acids and bases, and you should be able to identify their conjugate acid-base pairs from a reaction. And then the last piece, the strength of a Bronsted Lowry acid using kind of this chart that's been used over here. So hopefully that makes sense. If you do have questions, fill out that Google form, type them in there, and I'll do the best I can address them, or you can ask them in class. But if not, thank you guys so much. Look forward to seeing you guys again soon. Take care.